Hello everyone, welcome to session 3 of Data Structure and Algorithm series. In our previous discussion, we covered how the time complexity of an operation varies depending on the data structure and the algorithm used. Today, we'll dive into understanding growth functions and how they help us analyze algorithm efficiency of operations. Complexity helps us understand the efficiency of operations, particularly when dealing with large datasets. Time complexity tells us how long an operation takes, and space complexity tells us how much memory it uses. Back to how we measure complexity with growth functions. A growth function describes how the time or space required by an algorithm increases as the size of the input data, denoted as n, grows. This helps us predict an algorithm's performance with larger datasets. Growth refers to the increase in resource usage as the input size grows, and function is a mathematical way to represent this relationship. Let's compare two searching algorithms, linear search and binary search. Linear search checks each element one by one, taking up to n steps for n elements. Binary search divides the array in half each time, taking about log n to the base 2 steps. For n equals 1000, linear search might need 1000 steps, while binary search might need only about 10. Now, let's explore some common growth functions to fully grasp how algorithms scale. Growth functions provide a way to visualize how the time or space required by an algorithm increases with the input size. Here are some common growth functions. Logarithmic time, the time required increases slowly as the input size grows. Binary search is an example where the search time increases logarithmically with the number of elements. Linear time, the time required increases directly with the input size. Linear search is an example where the time required grows proportionally with the number of elements. Linearithmic time, the time required increases with both the number of elements and the logarithm of the number of elements. Merge sort is an example of this type of growth. Quadratic time, the time required grows with the square of the input size. Bubble sort is an example where the time required increases significantly as the number of elements grows. Exponential time, the time required doubles with each additional input element. The recursive Fibonacci algorithm's time grows exponentially as the number of elements increases. To sum up, different algorithms have different growth functions. Understanding these helps us predict how an algorithm performs as the input size grows. One thing to notice here, and perhaps it's clear by now, is that the faster the function grows, the worse the performance of the related algorithm is, as it takes more resources as the input size grows. To sum up, algorithms vary in efficiency, and growth functions help us compare these complexities. Remember, understanding growth functions is key to choosing the right algorithm for your data structures. In our next session, we delve into asymptotic analysis. Stay curious, and keep exploring. Happy coding!